This video is about power functions and polynomials. What are power functions? Power functions are functions of this sort. So a constant times x to a power n, and n should be an integer. So let's go back in here. What are the options that we get with that kind of function? So what I want to do first is to actually tell you approximately what the shape of these functions are. And then, of course, if you want to graph any of them, then you have to do a few plotting and a few points on it, and it would be more accurate. So before starting to do this, why do we start with power functions? Because power functions will give us idea about end behavior. And then the more important set of functions are the polynomials. And polynomials share the same sentiment of endpoints as the power functions do. So let's try to figure out how these power functions work. Let's say if n is odd and k is bigger than 0. So what sort of examples do we have with that? Examples, k is bigger than 0, so let's say number 3, and then x to a power that is odd, that would be, let's say, number 5. Okay, so how do we graph this type of functions? Something to notice in the example is more obvious. At x equal to 0, we will have a 0. And then for negative values, this entire thing is going to be a negative value. For positive value, this entire thing is going to be a positive value. The other things to notice is that when x is growing toward the positive infinity, the value of the function is going to grow to positive infinity. When x is growing to negative infinity, the value of the function grows to negative infinity. And so this is the approximate graph of the function for this type. Positive infinity, it's 0, 0, negative infinity to negative infinity. Let's do this one more time, like this. And it turns out that when this power is bigger and bigger, and how flattened it gets around negative 1 and 1 over here, it gets it becomes more and more flat around negative 1 and 1 over here. So let's say for x to power 3, it should be a little less flattened. And for x to power 5, let's say x to power 5. And for g of x equal to 5x to power 3, this is a little less flattened. Now, what about if we have n even and k bigger than 0? What would be an example? Example, y equal to 2x squared, or let's say y equal to another positive number. 1 is a positive number, x to the power 4, and so on and so forth. How does this end behavior work for this? First of all, again, notice that 0 and plugging in 0 gives you 0. Second is that doesn't matter if you plug in positive or negative value, it's always positive for any of them. And so let's graph a few. let's say for, and again, this is just approximate shape. You have to do a few plotting points to get, so let's say this is for y equal to 2x squared, and then for the second one, again, it would be a little bit more flattened, but the same shape. So with this one, as x goes to negative infinity, let's write it down. In this case, x goes to negative infinity, y goes to negative infinity, x goes to positive infinity, y goes to positive infinity. In this case, x goes to negative infinity, y goes to positive infinity, x goes to positive infinity, y goes to positive infinity. Now let's try the other ones. How about if n is odd and k is less than 0? If n is odd and k, what are the examples? Let's say y equal to k is less than 0, so negative x to power 3, or y equal to negative 5x to power 5, and so on and so forth. And in this case, if I plug in positive values in here, I see that I get a negative value, and if I plug in a negative value in here, I see I get a positive value. So it's sort of it goes this way rather than going that way with that one. So approximately, again, it looks like this. How about this one? N is even and k is less than 0. N is even and k is less than 0. As I plug in examples, let's say negative 2x to power 2. And then here, any value that I enter except for 0, any positive value or negative value that I plug in, and output is going to be a negative value. So in that case, it will look like this. So one thing that looking at the end behavior will tell us is when n is odd, if k is bigger than 0, the shape will be, the end behavior is like this. Right hand up, left hand down. When n is odd and k is less than 0, then it's the opposite way. The left hand is up, right hand is down. With the if n is odd and k is bigger than 0, n behaviors like this. When n is even and k is less than 0, n behavior is looking downward like that. Now we're going to try to use this to explain some polynomial behavior, n behavior, and graphing behaviors. So we discussed the power functions, and now it's time to discuss the polynomials. One thing that we said, it's about power functions. Again, power function give you the end behavior of polynomials. What are the polynomials? Polynomials are all the functions of this type. It's just made up out of all these power functions added together each, and these are called terms. These are term, another term, and all of them are, everything between pluses are terms. The one with the term with the highest power is called the leading term. And then the all these constants multiplying x to the power are called coefficients. And that one is the constant coefficient, the last one without an x. This one is the leading coefficient. And then the power of the polynomial is the highest power of any x in a polynomial. And here it would be n. So let's give a few examples. Example, y equal to negative 2x to the power 5 plus 3x to the power 3 plus 5. And here, the polynomial is degree 5. The leading coefficient is equal to negative 2. And then this would be also called A5. And if you notice, there is no power 4, so A4, the coefficient of the x to the power 4 is 0, and there is no x to the power 2, so A2 is 0, there is no x to the power 1, so A1 is 0. And the constant term is here. And then there are other things to notice in here. This polynomial is of degree 5, and then the leading coefficient is negative 2. If I want to figure out the end behavior of this polynomial, I look at power function with odd power and constant, the coefficient that is a negative value. Let's look at over here, an odd and k less than 0. So it's basically going this way. And my recommendation is always look at this coefficient will tell you the end behavior at positive infinity, this one. If it's negative, it's going to go down. And if the power is odd, then I either have this or this. And if I know that positive infinity, my right side goes down, then the other one should go up. So my end behaviors are toward negative infinity is that way, toward positive infinity is this way. Now let's give another example. Y equal to 2x minus 1, x minus 2, x minus 3 times x minus 4. This one is another polynomial, but oh, this doesn't look like that one. Why is this still a polynomial? And the best way to deal with this type of problem is just to remember, I can FOIL these two together, then distribute this one through the result of that foiling, and then distribute that one to the result of all of that, and then I get there will be any product between the factors. It would be just terms plus another term plus another term and plus another term. Now, how do I figure out what is the degree of this polynomial and what is the leading coefficient for this polynomial? Remember, degree comes from the highest power of x to the power n that you get. In here, if I'm looking at this, the highest power comes from multiplying this by this by this by this. And so x to power 4. So I know that the first term or the highest power is going to be 2 times x times x times x times x. 2x to the power 4. Then I will get a whole bunch of things, and the constant term is 2 times negative 1 times negative 2 times negative 3 times negative 4. That would be 12 times 2 times 2. That would be 48. So I can easily and quickly tell you the first and the last terms of this, and then there will be other terms coming in between. And so if you multiply them all together, you will see that, for example, this negative 1 can multiply by this, by this, by this, and it gives you negative x to the power 3. But is that the only x to the power 3 term that you get? No, there would be another one. Negative 2 times x times x times x times that 2 would be another one. So you have to do 2 times negative 1, negative 2 times x to the power 3 plus negative 4 times x to the power 3, negative 3 times, negative 6 times x to the power 3, negative 8 times x to the power 3. I'm sorry, I keep forgetting to multiply that through every time I say it. And so that would make up the term x to the power 3 with whatever coefficient that term has. But you have to calculate these. But it's easy to see that it's the highest power would be x to the power 4. What else is interesting in here? I can look at this end behavior, and I know because the coefficient is positive, a leading coefficient, and the degree is 4, degree is an even number, I will have this kind of end behavior. So I know that as x goes to positive infinity, it goes to positive infinity. As x goes to negative infinity, it goes to positive infinity. Again, this one tells you the behavior if this is positive at positive infinity, and then you have to decide whether you're going with the both of them up, both of them down, which is the even degree, or you have to go with this kind of behavior. So the next thing that I want to do is kind of discuss not detail of plotting the polynomial functions, but some details about how we interact with when we're graphing the polynomial functions. What do we know? What do we consider? Things that are obvious and we kind of want to have them in there for us. And then, of course, at this point, it's just plotting that we can use. When we get to calculus, there would be more tools. So I'm going to erase this and do a couple more examples, and then this video will be done. We're continuing with the power functions and polynomials, and we want to do a few examples of graphing polynomials. Example 1 is y equal to negative x to the power 3 minus 5x squared plus 6x. It's easier to just, in this case, to distribute that negative sign in and see what happens. So basically, this is, if I distribute, I would get this. One thing that we're looking for graphing polynomials is the zeros of the polynomial. Sometimes we're capable of factoring and finding those zeros. Sometimes it's not possible for us, and only numerical methods are possible. When we get to calculus, some of those numerical methods are going to be introduced. In a numerical analysis course, more of those numerical methods are going to be introduced. But at this point, all that we learned before about factoring, we can use it and factor these out to find the zeros of the polynomial. The other thing that is important for us in polynomials is the ups and downs, those local max, local min, that sort of things. Those again are a calculus situation, except for quadratic that I can tell you the vertex. That for other polynomials I can't tell you anything about the max or min of those polynomials, and that is left for calculus course. So even though I distribute that negative sign in, my plan is to actually factor this out to tell you all the zeros of this polynomial. What are the zeros? The only thing that this distributing that negative sign did for me is to tell me about the leading coefficient and the degree. Degree is 3, and then leading coefficient is negative. Therefore, I have to go to n odd and k less than 0 and have the expectation to look like this. So it would look like this shape. The end behavior would look like that. Now, how do I factor this? This is if I factor the negative sign again and I factor an x, I will get negative x times x squared minus 5x plus 6, negative x, and this factors into x minus 2 times x minus 3, right? Because 6 is 2 times 3, and so negative 2 times, or negative 2 times negative 3, and this one is negative 2 plus negative 3. So that works. And then what I can do is to put the zeros of the polynomial on the graph. One of them is x equal to 0. The other one is x equal to 2. And then x equal to 2. Then x equal to 3. And then I know about the end behavior. Right before the first 0, I can use that end behavior. I know it's going to be above the x-axis. And so I'm going to use the end behavior right here, bring it down to the first 0, and then first 0 is of degree 1, and so it goes through the x-axis, going to the second 0, again of degree 1. This should be a little smoother. Polynomials look, their graph looks very smooth. And then again goes through. And what I know is at x equal to 3 and on, I will have looking this way. Therefore, connecting it, I will get this type of shape. And again, smoothness is important. Going through all the zeros, if you can figure it out, is important. You need a few more points to plot this. If you cannot factor, only by plotting and many points, you can graph this function. Now, another function, y equal to x plus 1 to power 2 times x minus 1 times x plus 2 times x minus 2 to power 3. So first thing first, I can put all the zeros on the x-axis again. What is the degree of this polynomial? Let's say this one, the highest degree of the first factor is going to be x to power 2, then x to power 1, 2 plus 1, 3, 1, 4, 3 is going to be, and to power 3 is going to be 7. And then all the coefficients of x are positive, and here is just 1 is positive, therefore the leading coefficient is positive. So n odd and leading coefficient positive, therefore I will have this type of deal going on for me with that shape like this. And so the next thing is, what happens if I have zeros of degree bigger than 1? So what's going to happen is if you look at, for example, x plus 1 to power 2, that's the 0, negative 1 right here. The expectation is because just around the 0, you will get something of either this or that. Because degree of that 0 is 2, and 2 is an even number, and then you either will get this or that. And then it depends on when you're getting there, so you're expecting in here, you either get this or that. And in a little while, we figure out which one. In this one to power 3, you're expecting to get either around the 0, you're expecting either to get this or that. And it's not very flattened because it's only degree 3. That one is not very flattened either because it's only degree 2. If it was higher degrees, it would be more flattened around that 0. Now, how do I start? I know that at x equal to negative 2, this is the one that gives me negative 2, right? This one gives me 2, this one gives me 1, this one gives me negative 1. I know that at x equal to negative 2, the degree is 1, and I know that before, negative 2 is the lowest 0. I know that I start from negative infinity, and then I get to negative 2, and I'm supposed to go above. I'm supposed to cross the x-axis as negative 2. Then I know that at negative 1, I either go this way or that way. And negative 1 should not change because negative 1 was of degree 2. This sign is not going to change. Now it's obvious to me that the bottom one will not work. So I will have like this. And then at 1, degree is just 1. So I'll come back, I'll go down. And at 3 is going to add x equal to 2, degree is 3. So I will have like this. And I followed that and that end behavior and this end behavior as well. This actually helps us without knowing anything about the local min or local max. It tells us how many local min or local maxes can happen in here. And a lot of times in calculus, we learn that actually what we learn in calculus is that we learn how to figure out those local min and local maxes, and that those are helpful for us for optimization. That's another thing that we learn out of these things. The other thing that I want to mention is something to know is that smoothness. Do you see that there's no cusp or corners when I'm graphing, except there maybe accidental cusp and corners, and here also. Everything is smooth, and it's all with polynomial is supposed to be that way. There's no holes in between and the graph. That sort of explains the continuity. There's no cuts, there's no holes, there is no going to infinities inside the graph, except for the end behavior. These are things that to notice about polynomials and when you're graphing a polynomial. Next is an example where a polynomial is being used, and then discussing the intermediate value theorem.